Okay, so I had created 3 sequential videos, and I was mentioning there are, many different tricks, and not always would we go about it the same way. Sometimes I don't really see more than one option, but here are a couple more examples of how to solve trig equations. Okay, so one idea I had suggested is maybe making a u substitution. Again, I don't think it's necessary for this one, but let's look at how that would look algebraically. If I called sine x u, then sine squared would be u squared, right? And now this is a pretty simple equation of factor, I hope. Let's make sure it works. Plus 2 would be 2u, and then minus u, which does yield u. All right, so that works. So therefore, we get u equals -2 and u equals 1, but remember, we didn't have any u, right? We're solving for x. And u we made sine x, so sine x equals -2, sine x equals 1. Here's a red flag right here. Remember, the range of sine, right, if we think of the graph, the max was 1 and the min was -1. So anything outside of that -1 to 1 interval, we don't have a solution. So this is a dead end. But where is sine equal to 1, right here, that was pi over 2. Or you could think back to the unit circle. Sine is y, right? So it's that angle there, which is pi over 2. And you could substitute that back in and make sure, but that will work. All right, now, again, you don't need u substitution. Sometimes helpful, sometimes maybe just not really needed. But in this next one, when we try to factor, I cannot, right, let me go ahead and do the u substitution. I can't find a way to factor this. When we had that problem in algebra, we had to rely on the quadratic formula. So same thing here. If you didn't use the u substitution, right, you still have to rely on using the quadratic formula, but I don't think it's so obvious. So it has its perks. May not be necessary, but does have its perks. All right. So using u substitution then, I know this is b, right? A, b, and c is a -1. Substitute everything into the quadratic, we'd get -b plus minus square root b squared. So I'm just going to do that in my head. 4 minus 4 times a times c times 5 times -1. All over 2a, all over 2 times 5. I guess we could have done that in our head as well. That's okay. Okay, so we have 4 in the square root. 4, -4 times 5 times -1 is 20. So 4 plus 20, right? So we get -2 plus or minus square root of 24 all over 10. 24 breaks down to, well, 2 root 6, right? Because we have a pair of 2's and a 3 and a 2 left, so 2 root 6. I'm going to kind of skip one step in my head. So this is 2 root 6, and everything is divisible by 2. So therefore, we'd have -1 plus minus the square root of 6 over 5, right? Divided everything by 2 here. Okay, now we weren't solving for u, right? In fact, I didn't write it this time, but u we let be sine x, just like above. So therefore, sine x equals -1 plus minus square root 6 over 5. Now we're solving for x, and I want exact solutions. I don't really think, right, if this problem showed up and I got to this point, I am using a graphing calculator. I would probably graph this original equation here and see when it crosses the x-axis, right? See when it equals 0. The reasoning is I don't know when sine equals this, right? What I should make sure is if I did -1 plus square root of 6 over 5, it lies in the range of -1 to 1, right? Since that's where sine x, those are the possible values. And when I did -1 subtract square root of 6 over 5, it still stays within that range. Then we could use a calculator to do sine inverse if I guarantee that it does work. But here's the next problem. I have to make sure that, remember, sine inverse will only give values in quadrant 1 and quadrant 4, but the negative, right? It goes from negative pi over 2 to pi over 2. So I'm only going to get possibly one value of each of those. I would get this decimal answer, see where exactly that is, and then I would just think of, right, trying to stick within this range of 0 to 2 pi, domain for x, and think of 2 pi as about 6.28 and play around with it from there. Overall, in my opinion, this result, it warrants a calculator regardless. So I don't really see a need to find all these exact solutions. I would get to that point and know that there's nothing on the unit circle of those special angles on the unit circle, right? I need a calculator, go use a calculator. And in fact, I'd probably just jump right back to the start and graph that. Okay. So I'm going to put that one to rest. I did want to share, in case you run into that, that's kind of what's going on. And then we're playing around with values of whatever we get in the calculator, and knowing that, where exactly sine meets that criteria. I may end up adding pi or adding 2 pi to the result to keep it within 0 to 2 pi here. Alrighty, let's move on. Okay, this next two examples, I have sines and cosines. I want to include these because that's like having two variables, right? Like if I called sine x u, this would be u squared, and cosine squared would have to be v minus v squared minus u equals 0. I don't really know what to do with that. I have two variables, one equation, right? Like, dead end. Back to the drawing board. Use substitution. I don't know that that's the best idea. Next, I start looking at the table of identities, all the equations that we are given, and this is pretty close to, we have an equation that says cosine 2x equals cosine squared minus sine squared, right? And I could factor out a negative and make that substitution to make this negative cosine 2x. But now I still have the sine over here, right? So, I don't know necessarily where to go with that. I may need to go and check this identity out because it has several. So, you're not necessarily, right, like going in the wrong direction. Just maybe a direction I don't want to take. Here's often the trick with these. Okay, I think this is easiest. I have sines, sine squared, and a sine, right? Like, if I had them all sines, then it would look more like one of these previous equations where hopefully I could factor. Right? I didn't really like this one, but still you could solve. So instead, I'm actually going to use the Pythagorean identity that says sine squared plus cosine squared equals 1. And how I'm going to use that is I'm going to make this substitution for cosine squared is 1 minus sine squared. So I have a negative 1 minus sine squared, right? Since it's negative cosine squared. All right, if I'd made that substitution, I have all signs, and, well, I have a constant of 1 in there, but everything would be in signs and hopefully it factors. So let's give that a shot. Let's distribute this negative 1. So I'd have a sine squared plus another sine squared, so 2 sine squared. Then I have this minus sine x, and then I have a negative 1. All right, let's hope that this in fact factors. The first example I use substitution. Let's, we don't have to. Let's try to factor without it. So the only way I could get a sine is, 2 sine squared is 2 sine and sine. And the only way I could get this negative 1 is a plus 1 and a minus 1. I just got to make sure I have them in the correct order, which I think I do, but maybe not. So let's test. I'd have sine x minus 2 sine x. That would be sine x minus 2 sine x. That is in fact a negative sine x, so that looks good to go. Set each of those factors equal to 0, right? So 2 sine x plus 1 equals 0. Sine x minus 1 equals 0. So sine x equals a negative 1/2, and sine x equals 1. And let's see, where's sine 1? Sine is y, so that's at pi over 2. And then negative 1/2 is down here at this angle and this angle here. Right, sine is negative in quadrant 3 and 4. So those two, we get 7 pi over 6 and 11 pi over 6. So therefore we have 3 results. Pi over 2 is the smallest if I wrote them in order, but I'm going to just go ahead and state, right, there are my 3 results there. Alrighty. This last one. It's very similar to the one above, and we could solve it the same way by making this substitution, right? Change that to 1 minus sine squared. But I only have sine squared and cosine squared, so we could do that, get it all sine squared, that works. I could also make this substitution and put 1 minus cosine squared in for sine squared, and I would only have cosines. I could also, since I only have these two, make this a negative cosine 2x like we talked about in the first one, right? Where the first one we kind of, it would have led us through a revolving door. We'd have to make another substitution. It could have worked. But in this one, I only have, right, if I make that substitution, I only have 1 cosine. I'm good to go. Everything here can be solved. Kind of up to you. You have options here. And, not saying one way is necessarily better than the next. Yeah, let's go ahead and solve it. So we could say cosine 2x equals negative 1, right? Add cosine 2x. Where's cosine negative 1? Cosine is x, so that's right here at pi. But remember, that is just cosine x equals negative 1, right? Where x would be pi. But this is 2x, so I have to think actually like 2x equals pi, which means x is pi over 2. Because it's double the angle, right? If this is the angle, then 2x would be here. So we did an example like this where we actually had to think within 0 and 4 pi. So again, if we had x is 3 pi, because 3 pi is coterminal with pi, right here, and then here. we would get another solution. So x is 3 pi, and then divide that by 2. And we would get 3 pi over 2. And that is still within our original constraint of 0 to 2 pi. Alrighty. So we have two solutions. X is pi over 2 or 3 pi over 2. Cool. So I have this black squiggly line because I wanted to do just one more example. And you will notice this thing starts out looking quite horrific. We have seen problems like this in which it said verify, right? Verify the two sides are equal, verify the identity. But now we're actually solving this. So it's different strategy from before, or different finish, I should say. When you're verifying, you have to stick with one side of the equal side, right? You have to manipulate all this stuff on the left-hand side independently, oh, that's an S, from the right-hand side until you get two things that were equal. But since we're solving, this is an equation, I can now mess with both sides. So right away, why that's important in this example, I can just add this sine squared over here, and I see Pythag identity right away. Cosine squared plus sine squared is 1, right? Pythagorean identity. So now I just have this ugly mess here. I gotta solve that equation where that equals 1. I still think it's often best if you have tangents and secants and sines and cosines, like just try to change them all to sines and cosines, see what happens. Usually that's a great technique. So I'm going to go ahead and do that. Even though we have an equation, there might be an identity in here. I don't know. But I'm going to go ahead and stick with that. So tangent is sine over cosine. 2 minus secant is what? 1 over cosine, so 1 over cosine squared. Okay. Now, simplify this. First thing, I'm like, this is too ugly. Let's multiply by cosine squared over cosine squared. Okay, that's the LCD. I don't know if that's going to be best, but let's try it. So in the numerator, one of the cosines would cancel, and I would get 2 sine x times cosine x. In the denominator, I would get 2 cosine squared x minus 1, right, because those cancel completely, equals 1. Go and erase that. Now what? This thing is still quite ugly. Well, let's go and head in. It's an equation, right? So let's multiply this to the other side. Alrighty. And what next? I see this identity as that's a double angle. I see that as sine 2x. And it's not necessarily quite helping because of this cosine squared. But we could change cosine squared to 1 minus sine squared. Hopefully I'm not running into a dead end, which very well could be possible. Sometimes these are quite a pain, and maybe there's a simpler way to go about it. I don't know. But let's see. So now we have 2 minus sine squared x minus 1 sine 2x. Well, let's try. Oh, I forgot a 2 here. Sorry, 2 and 2, right? There's a 2 there. I feel like I am running into a dead end here. So let's rethink this. So I'm looking at the identities page here and trying to backtrack a bit. I found sine 2x. Okay, I think that one's going to be good to go. Ooh, here it is. Okay, and I'm not going to edit this video. It's okay that I make some things longer than it should be as well. I see this as an identity as well. Okay, this is a double angle. This is cosine 2x. I think that would actually help. So I'm not going to erase this because maybe not, right? Like maybe I need to revert back to that. Maybe I was onto something there, but I'm not sure. If the numerator I said was sine 2x, and the denominator I found an identity as well, cosine 2x, now I have sine over some angle. Cosine of some angle is tangent. Now I like that, right? That's now doable. Tangent to x is 1. So where is tangent equal to 1? Tangent is equal to 1 both here and here, right? Because tangent is y over x, and we want the same thing, right? The square root of 2 over 2 and square root of 2 over 2. And it's also true over here because tangent is positive in quadrant 3 because they're both negative. So we have pi over 4 and 3 pi over 4. Okay, but that is just x, right? We have 2x. So that means 2x equals this pi over 4. 2x equals the 3 pi over 4. And like before, we now really need to think in 0 to 4 pi for x, because 2x, right, our original answers have to be 0 to, I have this backwards, I'm sorry. Our 2x can be within 0 to 4 pi, but our x has to stay within 0 to 2 pi. So pi over 4, if I added 2 pi to this, that's 8 pi over 4, we have 9 pi over 4, right? And 3 pi over 4, if I add 2 pi to that, I'm at 11 pi over 4. Now I'm cutting each of those in half because those are 2x equals all of those results. So we have 4 answers. We have pi over 4 cut in half, so pi over 8. We have 3 pi over 4 cut in half, 3 pi over 8. Then we have 9 pi over 4 cut in half, that's 9 pi over 8. And then 11 pi over 4 cut in half is 11 pi over 8. Okay, that, like I said, I probably could have created a separate video for just this problem. Ooh, and I just looked at the answers and I'm off here. Plus 8. Oh, geez. It's not 3. This is just 5 pi over 4, right? Now I'm messing up on the basics. So that makes this here 13 pi. Okay. So not 3 pi, but 5 pi over 8 and 13 pi over 8. All right, good thing I checked that. But as I was saying, this is complex. Probably more than one way about it. I even got stumped, right? I didn't know where to go down here. Just kind of went back and looked at some of the identities again and noticed that one that stuck out to me. A lot of times you have some trial and error, right? The more practice, you habit these, the more tricks you gain, and the better you can solve them.